Champions! How you going? It's Friday Arvo. Why not do a video, or at least start one? This thing from above looks like something from the 50s, like some old radio or something, but it's just a dual rectifier solo head. Mesa. This one, it's 120 volts, you can tell by the tiny power transformer. The larger ones cope with 50 Hertz, this one's only probably suited to 60 Hertz. So it probably gets pretty warm even though we use a step down transformer, or the customer uses a step down transformer with it. So the initial problem was a pop and then no signal on this one. And I asked a little bit more about the use condition, and he was, the customer was recording through the line out without having it plugged into a speaker, so that's a big no-no. He knows now. You don't know until you know. Now you know. So there you go. The most obvious thing, one of the outputs has lost vacuum, so they've got a thing called a getter flash, which is a little ring of metal inside there that's got a metal plating on it. And the last thing they do after they suck the air out of the valve, or all they can anyway, you can never get a perfect vacuum, then they hit those little rings. You can see down in there, actually they're different types of valves. This one's the odd one out. That's a, I only just noticed that then. That's a wing C. That's a Sovtech. So what do we got? We've got, that's the odd one out. We've got three Sovtechs, Svetlanas. 3 Svetlanas and 1 wing C. So yeah, I just noticed that when I looked at the getters because they're different. So anyway, you can see inside there, there's those little discs in there, little dish things pointing up at the glass. And on this one, it's got a ring. Usually they've got a ring. That gets hit with an induction heater from outside the valve, heats up, and then the plating on it evaporates and condenses on the glass. Now it has two functions. It absorbs the last of the oxygen in the glass, in the valve, sorry. And if it does lose vacuum in the future, it tries to absorb the universe and it can't, so it turns white and changes to another compound. It oxidizes and turns to that flaky white crap stuck to the inside of that bulb there. So that means that one's lost vacuum. That may not be the cause of loss of signal because it hasn't blown a fuse. Now, Mesa Boogies are, I don't know how they're legal to be sold in Australia because they've got no secondary fusing at all. As far as I knew, in Europe at least, that's a legal requirement, so I don't know if they've got a separate power input board that they use in Europe. But as far as I knew, in Europe you had to have secondary fusing of everything, because you see like PVs and well, you know, anything from Europe, and every single winding has a fuse on it. Like even the bias tap will have a fuse on it, which is not great. There's a Fender 300 watt Bassman, which is all valve, well not all valve, but runs what, like 6 6550s or whatever it is. Even that, its heaters has a massive fuse on it, like I don't know, a 20 amp fuse or something ridiculous. Like there's no point having a fuse, it just burns out the fuse holders. So yeah, pretty much everything has secondary fusing, and then Mesa Boogie don't even have a high tension fuse. So you know what the fuse is when you don't have a high tension fuse? The fuse is either the primary fuse, if it hasn't been swapped out for a higher value or wrapped in foil by the user. And since it's accessible from the rear, that's very common. Oh, we just need it going for this gig and then I'll worry about it later. Yeah, well, you just set fire to the inside of your amp. So this thing needs a big clean. But yeah, back to that point. If you don't have any secondary fusing, even on your high tension, which is very much advisable in an amp design, the next fuse is your circuit board. So you blow traces off the board, you explode diodes, you burn wiring, you set fire to the inside of your amp, and that's what Mesa Boogie seem completely content doing because they never fuse the high tension. So what we have here, I couldn't find any initial severe damage. There's no obvious burn marks or no discoloured components. I've looked pretty closely at it. Couldn't find anything that would have caused a complete loss of signal, which the user reported. He said it cut out. The mains fuse is fine, it's 4 amp. Remember, that's 4 amp for 120 volts, not 240. That would be 2 amp for 240 volt. But it's got a single winding on the primary, so we can't rewire this one for multiple voltages. So it would either be a transformer replacement or he has to continue using a step down transformer. So the other thing I saw, well, sorry, I said I didn't see anything discoloured. The screen grid resistors have gotten hot, but all 4 of them have gotten hot. The colours have changed. So let's just see what resistance they're running at. See what resistance they're sitting at. They're not running anywhere. They're just under a K. Okay. Oh, sorry, I was shorting out on the bus there. And that one's just under a K as well. Just under a K. And just under a K. So they're all correct. They are discoloured though, so we'll investigate that further. I doubt there would have been a fault in all 4 valves, but they look like metal oxide 2 waters, so they should probably be 5 waters, like you'd find in most amps this power. So what I reckon we do is, just with the valves out, we'll run it up on the Variac and we'll just see the voltage is everywhere it should be. We're not going to go to full voltage because then we'll exceed the value possibly of the caps because they're not loaded. So we'll just run it up slowly, just check that all the voltages are a proportion of what we expect given the input voltage, and we'll go from there, I guess. And we've got a new set of valves ready to go, and if we can't find anything drastically wrong, we'll pop in a new set and we'll see how we do. So that confirms that there are 120 volts AC, 60 Hertz. So if you've got a transformer that's capable of dealing with 60 or 50 Hertz, it'll say 60/50 Hertz. The core size has to be bigger to deal with the lower frequency, otherwise the transformer saturates earlier and doesn't hit its rated power output at 50 Hertz. 60 Hertz, because it's a higher frequency, you can have a smaller transformer core. If you look at switch mode power supplies these days, you've got these monster power supplies in like 1000 watt base amps, and the transformer's like, you know, it's not much bigger footprint than a packet of Tic Tacs, right? That's because it's switching at like 100 kilohertz or higher. The core size is proportional to the power as well as the frequency that it's transforming. The higher the frequency, the smaller the core you can have. So on the back here, it's got vacuum tubes, normal, silicon diodes, high power. So that's choosing which rectifier you're using. It's just bypassing the rectifier valves, the 5U4s. It's got 2 5U4s in it in parallel, and they appear okay. We'll see. Obviously you've got your fuse there, which I've taken out to check, and you've got a spongy / bulb switch. Now that changes to a lower voltage, well, a higher voltage tap on the primary actually. So on bulb you've got your full power, and then when you go to spongy, it adds, I believe it adds more windings, so the primary is has got greater turn ratio to the same amount of turns on the secondary. So the effect is when you're on spongy, all your voltages are lower. That's not great either, because that's kind of dumb, because you want your high tension to change, but you don't want your heater voltages to change, or the voltages going to your relays and your switching circuitry and all the low voltage stuff. So again, it's gonna be fucked while they do that. Stuck in their ways. It sort of kind of works, so that's good enough to just keep doing it for 50 years for Mesa. There's better ways to do it, but whatever. Does the job, I guess. You'd like, for the amount of money you pay for these things, you'd like a little bit better than does the job though, wouldn't you? But whatever. Alrighty, so here we've got your typical Mesa construction. So we've got some hard wiring, we've also got a circuit board. You've got the valve sockets all hardwired. They've got like bus wire between them for the common connections, like heaters and the paralleled rectifier valves down there. You see it's just literally like 18 gauge wire going between the corresponding pins. Nothing wrong with that. It's reasonably sturdy. It makes changing stuff a bit difficult because you've got to pretty much cut the wire and rerun it again, do a new sort of loom, or cut a section out and redo it if a valve socket needs replacing. But you know, that's pretty rare. Well, not rare, but you know, don't really build for ease of replacement of valve sockets. Well, no one else does anyway. So you've got the usual sort of Mesa layout, no real rhyme or reason to it. Just looks like someone spewed up components on a board and then connected the wires to each other. The traces. So there'll be a part over here that's connected to things over there that has nothing to do with stuff over here. It's just over there because they had a gap, and then they run all the wires over to it. It's quite hilarious if you've ever laid a board out and you actually look at one of these and you think, what the hell? But again, it's Mesa, they're never going to change, just deal with it. So it looks to me like they still don't really use computer-aided design on their boards. It's almost like it's still laid out with tape and like photoresist. Surely not, but these boards look like they're from a computer in 1982. No one else makes boards like this anymore. I haven't seen anyone make boards that look anything like this since 1982, except Mesa. So I don't know if they might make them in-house. I don't know. There's got to be some reason behind it, because it's just so antiquated and illogical. Like, you'd think that you'd be just using modern manufacturing technique for a world-class amp manufacturer, but I don't know, there's got to be more to the story. So the biggest problem with Mesa PCBs is the traces are way too thin and the pads are way too small. So essentially the pads are not a lot more than a tube. They're through-plated, so that's their saving grace, but essentially the pads are not a lot more than a tube that goes on the inside of the hole. So you can solder to them once, and if you solder to them again, it's very likely that the pad goes bye-bye and you just end up with the tube in the middle of the hole for the through plating. And that's tricky to solder to and not very sturdy, so you've got to be super careful. If you've got to remove a component out of a Mesa, it's better to cut the actual leads and pull a lead out from the bottom, because if you try and pull a component up from the top, like all amateur techs do, none of them want to remove the board. They all want to just change one part, be the superhero of the day, charge like $50, right? You're pretty much guaranteed you're going to pull that pad out, and you possibly could pull the whole through hole plating out in the process too, particularly if you don't have a very well controlled temperature on the soldering iron. So don't do that. So everything's pretty cramped. You've got components that live in the circle on the bottom of the valve base, on the preamp valves. So you've got what, 3 components there on that, in that valve circle, valve footprint. You got 2 components there, a resistor and a cap. You got 3 components there, 2 resistors and 1 cap. Now the other thing is they use a lot of tantalum capacitors in Mesa Boogie amps in various places, most commonly, excuse me, on the cathode bypass of each preamp gain stage. So they're known for going short circuit if they exceed their voltage rating even by a tiny bit. Electrolytic capacitors are a little bit more sturdy. They can, there's a party or something happening outside. I want to go investigate. It must be beer o'clock. Well, it's 4 o'clock on a Friday, so yeah, probably. If you go marginally above the tantalum caps rating, it goes short circuit. That can happen by a shorted valve, a spike in the power, various things can cause it, and then your cap goes short, whereas an electrolytic is much more tolerant to that. So just to continue the Mesa bashing, at the risk of being cynical, another thing they do which makes it pretty expensive and annoying to work on, since the circuit board is rather delicate, if you want to change one of these resistors down here, well, look what's on top of it, a capacitor. So to anyone that's done circuit board layout, using KiCad or whatever EDA software, to sort of give everything its own footprint. This, whatever you call this layout, they put components on top of other components. It's not an actual footprint for the part. Multiple parts share the same holes. They don't make the holes larger diameter, so they just put the leads on top and build a fucking tent out of solder up to the lead. It's not state-of-the-art circuit boards, let's put it that way. So if I was to change one of those resistors, basically I'd have to remove at least one cap, possibly two, and then risk damaging their circuit board holes as well, because the circuit board's so delicate and the pads are so tiny. It's easier to cut the leads, but then you can't reuse the cap. So to change one resistor, you're probably paying for one resistor plus two caps plus 15 minutes, and that just adds the cost up. I call it the Mesa tax. You bought a Mesa Boogie, now you got to pay to maintain it, and they're not designed to be repairable easily. It's all repairable, but it's just time consuming. You've got like a resistor there whose leads disappear down under that cap. You've got this cap leaned over to make room for that resistor, so that resistor can make room for that cap. If they just laid stuff out properly, you wouldn't have those issues. And they stack their opto couplers on top of each other, so you have like 3 or 4 optos stacked up, you can see down there, and they all share the same holes down there. Because the leads are too big to go through one hole, they just goop them all together with solder and hope for the best. Yeah, again down there, like how are you supposed to... There's actually a resistor under there, can you see it? It's hiding. How are you supposed to replace that? You can't, you got to remove both those caps to get to it. So not only is fault finding fun on these things because everything's hidden away, you've got to remove extra components to get to the one that you need changed. So yeah, I mean, like, all of that could have been solved if they went with radial caps instead of axials. That would have freed up a lot of real estate on the board. You wouldn't have to squeeze things together so much. But like the density of the circuit board isn't consistent either. It is on some others, they're so jam tight, but like these gaps where you've got traces snaking back and forth, if you use a computer aided design package, it does half the work for you. You'd be able to have a much more efficient layout, much more logical, much shorter signal line lengths, optimize your heater layout for the preamp valves. Sky's the limit. Like, move on to computer aided design, Mesa, please. Like, it's time. It's 2021. We've got billionaires just flying in space for the fun of it. You can do it. Come on. So I think the first thing we do is just give the thing a good clean on the top. The sockets, you can see all the pin contacts are pretty tarnished. They've gone a blackened colour. The pins on the output valves don't look too bad, but if we look at the preamps, they're all like black. They're like a black, sort of like a matte black sort of hue. Okay, so my camera has stopped focusing on anything. I think it's time for a new camera. It didn't last long. There we go. So you can see how blackened those pins are. We'll see if they clean up, but they are the original valves too, so we'll clean them up, we'll check their functionality, and if need be we'll put some new ones in there. Transformer's a bit loose too. Have to look at that. I think they're just self-tapping screws, so yeah, they're just like Fender, they love using self-tappers. So what we'll do is put some proper M4, probably M4 machine screws through, and if we've got to remove the board, because 2 of them are under the board, so we won't be doing that unless we can get under there. But yeah, ideally you'd have like M4 to M5 screws and lock washer and a nylock nut on the bottom. So let's just check the primary of the output transformer. We'll just make sure nothing's open circuit there. So we've got the red lead goes to the center tap, and we've got the blue there, 37 ohms. We've got the brown there. Oh, is that brown? Yeah, brown. About 35 ohms, so that's pretty good. It's about what you'd expect, DC resistance. A lot of guys measure that and freak out because they go, oh, it's supposed to be a 1500 or 1.5k or whatever primary. Well, that's DC resistance. That's at 0 hertz. The DC resistance and the impedance are drastically different measurements, but on a high current 100 watt output transformer, that's about right, 30, 40, 50, 60 ohms, whatever. If one's way out to the other, that's a problem. If one's open circuit, that's a problem. Or if there is a short to ground, that's a massive problem. Bear in mind that the DC resistance will be less for whatever side of the center tap is on the center of the bobbin. Now it goes off a turns ratio for impedance, but for DC it's just literally the length of the wire. So the inside will have the same amount of turns but a shorter length, obviously, because it's like running the inside track on a running race, right? Not that I've done that for a while, but anyway, one day. So the inner coils are shorter length, so lower DC resistance, and the outer coils are longer, so higher DC resistance, but they'll be the same or approximately the same impedance, so nothing to stress about there. I see that a lot on forums. One side's 20 ohms, the other side's 30 ohms. It's fine. As long as you don't have anything open circuit or any shorted windings, which would load it down significantly. Or a short to the actual like the casing, the laminations of the transformer, because that would give a dead short to ground. Just doing a little bit tedious bit of cleaning the top of the chassis. So the vent in the top of the cabinet, it just lets dust and stuff through. You need it there for ventilation, but it just ends up with a little shadow of dust right where the vent is on the cabinet. So things get a bit gross, and people sit drinks on their amps, and inevitably there's a spill or two in there, and same old story. But it's cleaning up alright, considering it's a coated chassis, unlike the Marshalls, which are like a zinc chromate coating, which corrodes and looks pretty manky over time. These ones actually clean up okay. A little bit of slightly damp rag. There you go, it's a bit nicer, isn't it? I've taken off the retainers, partially just so I could get access to clean the chassis nice and good, nice and proper and good and stuff. I'll give them a little bit of a clean, but in the meantime I'll leave them off because they just get in the way of the bias probes, and I want to just check that everything's running and leave it under load for a little while and just make sure everything's stable, providing there's nothing obviously wrong with the thing. And even after if we do find something after we've repaired it, I still put it under load for a while and just make sure that everything's stable, and then we can be confident that there won't be any immediate problems. Now, to do our initial test, we have to put the rectifier valves back in at least, otherwise we won't get any high tension when it's switched to the rectifier. This guy brought it in with it set to vacuum tubes, set to rectifier. I did make a note of that when it came in. So we'll have to check both, but you know what, in the meantime we'll just run it with the silicon diodes just to check everything's in line, because we won't have to wait for the heater to warm up. There'll be more linear voltage output as we ramp up the Variac, and then afterwards, once we've ensured there's nothing wrong with the actual amp, we'll test the rectifier valves in there as well. Well, just one thing at a time, you know. That's how you eliminate stuff. You don't try and find 6 possible solutions at once. You just work your way through process of elimination, starting with the power supply every time. One thing I forgot to show you. Power switch. That's how it came in. I always said messes are the devil's work, eh? I don't know what that was even off. The end of a pencil or something. We'll get rid of that for now. Alrighty, champions, we'll flip the back over. I've got the Variac. Lick me. Variac shitbox. You can see there. Took me 3 of them to get one that worked. I should have just bought a good brand, but false economy being what it is, I didn't. Speaking of shit, fluke leads. You got a $500 meter. I think they go for $650 or $600 and something. The 179s do, which is that one over there. You pay another $200 for a thermometer, which you never use, and a backlight, which you can't even see. So just get the 175, people. That's the backlight. Let me turn the light off. Oh, we'll do a little impromptu multimeter review while we're at it, eh? Can you see the backlight? Yeah, me neither. So yeah, that's what another $200 gets you, but I think at the time the 175 was out of stock for some time, so I went with the 179 anyway, and I used the thermometer for smoking meat, so hunky-dory. It's got the min-max setting too, so you can set it to go off alarm if the smoker gets too hot or cold. Talk about multi-purpose. So, where was I? Oh yeah, so fluke leads suck. So that's them there. They're like moulded crap. Everyone says in the advertising that these are silicon leads, but they're not. They're PVC. They're not very flexible, and if they touch your soldering iron, they melt. So I'm yet to find a reasonably priced, really good set of multimeter probes. I thought I was onto some. I got these from Wes Components, the retail outlet being Wagner Electronics here in let me start again, eh? Wagner Electronics here in Australia. They're at Some Hill in Sydney. So they're sort of no-name things. I think they're a rip-off of Pomona or someone. Someone has one that looks like that but cost about 3 times as much. I only found that out after I bought these. These were still like $25 or something, but proper silicon, like you can wrap them around your soldering iron, it doesn't hurt them, so that's cool. I thought they were really good until the other day. I was fault finding an amp and nothing was making sense. I'm like, what the hell is going, what am I missing? And then touched the probes together and it was fine, but then the resistance jumped through the roof and I hadn't removed the probes yet, and I'm like, hang on. So then I held them together, wiggled the back end, and yeah, sure enough, there was a conductor failure within that little section of the handle there, which is quite common on probes, being the point that bends the most as you're working with them. You know, they get rough treatment, but really good quality ones use like a form of Litz wire inside, which is super flexible, and instead of soldering the things, they actually crimp them well within the actual body of the probe, so there's no flexibility where the actual connection takes place. So yeah, I've bought a few more expensive, like $50 to $100 sets. I might even do a review of them, I guess. So yeah, stay posted for that. They're readily available from the major distributors, not eBay or anything like that. I don't buy anything off eBay if I can help it, and you shouldn't either, because you're a serious tech. That's why you're watching my videos. It doesn't add up, does it? So anyway, so cause we have a Variac capable of pumping it up, pump it up, come on now to 260 volts. We really don't want to do that. We're going to carefully monitor the voltage using an actual multimeter, because this does have a dodgy meter on the front butt. I didn't mean to say that. On the front, but it's not very accurate. I wouldn't be trusting that little piece of Chinese crap. Nothing against China, but it's a low price point, and yeah, it's not an accurate measurement device, particularly in the non-linear region as it goes up towards the higher voltages. So always monitor it with a quality multimeter. So that means a real fluke, not a fruit. And well, basically the gist of what I'm swinging at you is, if you can't trust your test gear, what can you trust? It's your reference. And if you can't trust your reference, well, you're just shooting in the dark. And I know that's how some of us came to be in the first place, thanks to our parents, but okay, enough of that. So I'll plug that in, and what I've got here is a piggyback. Real technical thing here. So I literally go probes in there, shove them in the piggyback, set your meter to AC volts, not AC amps, plug that into the Variac, turn it off first, yeah, plug that into the Variac, and plug the IEC lead into the amp. Alrighty. Now we've got our fuse somewhere. Where is it? There it is. 4 amp fuse. If you're real worried, you can chuck an underrated fuse in there, just as you're doing initial testies. Oh fuck! I didn't mean to say that either. Friday, I've got to go home. I'm going to make a fool of myself more than usual. So you can put like a 1 amp fuse in there if you're worried. That way the fuse will blow well before anything goes wrong. Just be aware of the inrush current, but ramping it up slowly on a Variac, there is no inrush current. So we'll switch our power and our standby on. We've got no valves in there. Now when you've got no valves in there, be careful not to push the voltage up to normal operating voltages, because well, with no load on the amplifier, the voltages will be higher than usual and they'll exceed the cap ratings as previously mentioned. So what we'll do is ramp it up slowly, and just, you know, we'll get the AC to, I don't know, like 20 volts, and because we're not relying on anything warming up, because all the valves are removed and we're switched to the silicon rectifiers, we can look through and see if you know, we've got a negative voltage of some description on the bias. If we've got you know, all the high tension will be about the same level all the way through, so you won't get your dropping, because the dropper resistors are just half of a voltage divider, and the other half of that voltage divider is the tube itself. So there's no bottom on that voltage divider, so everything that's unloaded will be about the same voltage all the way through the amp, all the way to the first preamp valve. So we can just make sure there's no breaks there. We won't get any indication of how the droppers are dropping. So if a resistor's breaking down under high load, we won't be able to tell that, but we'll be able to tell if one's fully open circuit, and we'll be able to tell if there's a short anywhere to ground. So we'll suss that out. So speaking of leads, I did buy some just lengths of silicon wire, specifically test lead, 1000 volt silicon jacketed black and red wire from RS Components, and it's really good quality stuff. It's really, it doesn't have a memory to it, so you can roll it up, you could, you know, bunch it up and it just goes straight again. The PVC remembers all its bends and it's annoying because it like bunches up when you're trying to stretch it out. So yeah, that stuff is really good. I might put a link to that in the down below, doodly-doo, or whatever AVE says in the doodly-doo, down below the video. So anyway, I've got this is my alligator clip. I plug that into the common, connect that to a convenient ground point. For example, that wire right there. And now we've got one red probe, reference to ground, that we can use to check our DC voltages, or flick it over to AC and check our AC voltages, just to confirm that everything's working as it should. So let's fire it up. We're on 0 volts, which isn't really 0 volts, more like 4 volts. So we're on 4 volts AC going in, so that's where it would be expecting 120. So let's just have a little probe around and see what's going on, eh? So we've got our rectifiers over here. Everything, both switches are on. Itchy nose, sorry. It's our B+. We've got 12 volts on there. We've got our bias feed, which is there, minus 1.4, so we've got a negative voltage where the bias is, so that's good. Our screen grids, we've got same as B+, 12.5, 12.5, 12.5, all the way through. And we'll just check, it's a real pain in the ass to get to these preamp valves because they're covered in crap. 12.5, so that's V1A plate, and that's like 12.25. Alright, so there's one unused triode there, I forgot about that one. That's V1B, so all the pins are grounded there. It's actually a little grounding point as well. So on the next valve, which you can't see easily, which is there, so pin 1, 12.4, pin 6, 12.4, 12.4, 12.5. Yeah, look at this, like. So we're just trying to get to this valve at the back here. It's got that is the bottom of the valve socket. So you got one resistor, 2 Vactrols stacked on top of each other, and then a bunch of caps overlapping that valve socket. So to get to pin 1, you got to reach under there. You can easily short out to either side there the plate voltage, and then you'd have full plate voltage on that Vactrol there. So to probe in there is just about impossible without shorting anything out. So what you can do is get a bit of heat shrink, put it on the probe, just so the very tip's poking through, and then you're a bit safer probing around in that kind of environment. So let's do that. So if you're wondering where pin 6 is, you've got 1 under there, 2, 3, pin 4 and 5 joined together there because that's a heater. Pin 6 is sandwiched between those 2 resistors, and my probe can't even touch it because it's not sharp enough. Like, that's putting a lot of faith in the tiny little enamel coating on those resistors too, like having that pin sandwiched in there. It's just shit layout, honestly. There's no other excuse for it. It's just, but you know. Right, so let's jack the voltage up a little bit. Let's go up to like, I don't know, 50 volts. See if anything blows up in our face. As we go, we'll just keep checking voltages. Make sure nothing's breaking down. So that's 120 odd volts on the B+. Same everywhere because nothing's loaded. Except the guy who designed it. So let's go up to 50 volts. That's AC on the input. I just heard something click then, so one of the relays responded. Hear that little click? It's got a hysteresis to it, but that indicates that the low voltage supply is working. So no need to track that down just yet. I reckon we throw some valves in there. Keep an eye on the dissipation. I'll just check the bias first. We'll go back to 50 volts. Bias feed, we'll just look at the grids actually. -17 on that side of the grid stopper. -17 on the valve side of the grid stopper, so the grid stoppers are fine. At least at this point. Yep, so everything's getting biased, so that's cool. So let's put some valves in there and we'll slowly ramp her up and see how she reacts.